section. So we have this section and then one more, and then you'll have another quiz. So moving on here, a sample space is the set of all possible outcomes in a distribution. Consider a distribution of values represented by the sum of the values of two dice and a distribution of the miles per gallon for a sample of cars. So here we have the sum of two dice. So if you roll those two dice, if you add them, you have the least possible chance of getting a 2 and a 12, most possible chance of getting a 7. Okay, so we're looking at these kind of probabilities here. The sum of the values on the dice can be any integer from 2 to 12. So the sample space is 2, 3, 4, everything up until 12. So we will have to be able to find that when we move on in some of our examples. This distribution is discrete, okay, because the number of possible values in the sample space can be counted. So when we can count how many or count that sum, it is called discrete, it is finite. Okay, the distribution of miles per gallon is continuous, okay, hence the different graph up here. Well, the sample space includes any positive value less than a certain maximum, around 100. The data can take on an infinite number of values within this range. Okay, so this one is finite. We just have these bar graphs right here. This one, we can have a range of values as it goes up and then back down. The value of a random variable is the numerical outcome of a random event. A random variable can be discrete or continuous. Discrete random variables represent countable values. So again, discrete, we can count how many there are. Continuous random variables can take on any value. Okay, so we are going to go through the different types here. So labeling these as discrete or continuous. So in example 1, identify the random variable in each distribution and classify it as discrete or continuous. So letter A, we have the number of hits for the players of a baseball team. So are we able to count that, or is that continuous? You can count it, okay? So this one will be discrete. But first I want to identify the random variable. Okay, so we usually use x as the random variable, and that is the number of hits for each player on the team. Okay, so identifying that random variable. Now we did say it is discrete, okay? So since this is countable, x is discrete. Okay, and again, we just use x as that random variable. Okay, then letter B, we're doing the same thing, so identify the random variable and then say whether it is continuous or discrete. So letter B says the distances traveled by the tee shots in a golf tournament. It is continuous. Okay, what's the random variable in this case? Yep. So x is our random variable, but what is it? So what would... Yep. By each tee shot. Okay, and then we did say it was continuous. Okay, so since this could be any value within a certain range, x is continuous. Okay, so that graph would again look more like that miles per gallon graph, because it can take on multiple values. Okay, questions on identifying those ones? Not too bad. All right, then moving on here, a probability distribution for a particular random variable is a function that maps the sample space to the probabilities of the outcomes of the sample space. Probability distributions can be represented by tables, equations, or graphs. In this lesson, we'll focus on discrete probability distributions. So we're looking at the ones that are countable. Okay, so we can count the sum or what that probability could be. Okay, so for our probability distributions in this table here, we have a probability distribution can be determined theoretically or experimentally. A probability distribution can be discrete or continuous, like we looked at already. The probability of each value of x must be at least 0 and not greater than 1. Okay, so your probability has to be between 0 and 1. It can't be negative, and you don't want it to go over 1 because that's over 100% probability then. Okay, the sum of all the probabilities for all of the possible values of x must equal 1. So if I were to add up each probability that I find, it should equal 100%, so that would be 1. Okay. So if I look at my next page here, a theoretical probability distribution is based on what is expected to happen. For example, the distribution for flipping a fair coin, for the probability of heads is 0.5 and the probability of tails is 0.5. Okay, so that is theoretically what would happen. Now, if you were to actually do that, in some cases you might get a higher probability of heads just because it is randomly done. So in example 2, we are going to construct a relative frequency table. So we're going to let x represent the sum of 2 cards drawn from a stack numbered 1 through 8 with replacement. Okay, so that means, I have my nice handy dandy cards here, 1 through 8. If I were to draw 1 card, okay, I got an 8, right? With replacement means I put it back before I draw my second card, which is an ace. Now, we're going to take the sum of those 2 cards, which in my case would be 9, and we want to do that for each combination. Okay, so we want to write out each combination of what I could draw out of that deck. So in the top here, we're going to find the sum of the 2 cards together. Okay, in that second row there, we're going to find the frequency with which it happens. And then the last one is the relative frequency, which I suppose, right? Or probability. Okay, so first row, we want the sum. Well, if I have to draw 2 cards with replacement, my lowest sum would have to be what? 2. Okay, I could draw a 1 and a 1. So I have to replace that 1 back in the deck. Okay, then next I could have a sum of what?
3.
3. 4.
5, 6, 7.
Yep. How far will it go though? What's my highest card?
8.
My highest card is 8, so what should my highest sum be? 16. Okay, so I could draw cards and get all of those different sums there. Now we want the frequency. This one is a little bit more challenging. So in order to get a sum of 2, how many ways could I get a sum of 2 by drawing my cards? Only one, right? I'd have to draw 2 1s in order to get a 2. Now to get a 3 or a sum of 3, how many different combinations could I have?
Draw 1 and then a 3 or then a 3 card.
Yes.
1 and a 2.
So I could draw a 1 and then a 2, or I could draw a 2 and then a 1. Okay? So I have 2 different ways that I could have a sum of 3. Okay, now if I look at a sum of 4.
1, 3, 4,
3. I could draw a 1 and then a 3. I could draw a 3 and then a 1, or I could do a 2 and a 2. But 2 and 2 is the same as 2 and 2, so that only counts as 1, not 2 different ways. So this one would be 3.
Let me guess, 4.
It is 4.
Oh boy.
Okay, so to get a 5, I could do 1 and 4, 4 and 1, 2 and 3, or 3 and 2. Okay, so there's 4 ways. It does go up by 1 until you hit what number?
15. 14.
9.
10. 13.
So for a sum of 6, you have 5 different combinations. Sum of 7, you have 6. Sum of 8, you have 7. Sum of 9, you have 8. But with 10, it's going to start going back down.
7, 6, 5.
Yeah. So with a sum of 10, you have 7 different possible ways. 11 is 6. 12 is 5. 13 is 4. 14 is 3. 15, 2. 16, 1. 9. The median. It is the median because it's in the middle. All right, then to find the probability of each.
So we have to write 1 out of 6 or 1 out of 15.
So it is 1 out of something. Okay, so we want to look at how many total combinations we have. That would have to do with the frequency here. So we need to add up every single one of these combinations and what that total would be. Okay, that total is 64. So to find my probability for a sum of 2, I take that frequency of 1 and divide by how many different combinations I have. So 1 out of 64.
Do we have to write this in decimal or can we just
I am going to write it in decimal.
do we have to?
No, but to graph it, it'll be a little bit easier if you write it in decimal. So all I did here was take 1 divided by 64 to get 0.02. Okay, we'll do the same thing with a sum of 3. There are 2 possible combinations for that. So to find its probability, take 2, divide by 64.
Do we write it would we write it as 137? Not in this way.
You can reduce it, yeah. Okay, so I have 0.03 as my probability. Next one, we have 3 out of 64. No.
Ah.
Then 4 out of 64. No.
8. 7. 4.4.
Then our sum of 6 is 5 out of 64. Okay, 5 out of 64 is 0.08. Did you get the pattern yet? Next one is 6 out of 64. Yeah. Okay, next we have 7 out of 64.
Picture. Yeah.
Okay, probability of getting a sum of 9 would be 8 out of 64.
What'd you pull? 0.14.
No, this is where it changes. Okay, then it does go back down. So since I'm starting at 7, I have 7 out of 64. We already found that one. That was 0.11. 6 out of 64 was 0.09. 5 out of 64, 0.08. 4 out of 64, 0.06. 3 out of 64, 0.05. 2 out of 64, 0.03. And then 1 out of 64 was 0.02. Okay, so again, we are just finding the probability of each of these different sums when I'm drawing a random card with replacement. Okay, it would be a little bit different if I didn't replace it, so keep that in mind. Next, after we create this relative frequency table, we can graph the theoretical probability distribution. So we just have to use our random variable x, which is just the sums, and then the probability is your y-axis along this table. So creating this nice graph, we have our x, which is our sum. Okay, so our sum is going to go along that x-axis, and then our probability is going to go along the y-axis. Okay? So yes, you do need to label that graph. Okay, sums along the x-axis, probability is along the y-axis. So all we have to do is use our table above. So we have all of our x values here, 2 to 16, that have to be plotted along this line. And then our probability are all of these values that have to be plotted along here. So since my highest probability is 0.13, I'm just going to go up by 0.02 each time along the y-axis. So if I start at 0 here, I could go up to 0.002. Then go up by 0.02 each time, have 0.04, 0.06, okay, when you go from 0.08 to 10, remember it's 0.1 then, not 0.010, okay? Then I have 0.12, 0.14, 6, 0.18, and 0.2. Okay, now with your x values, that's your sum. Okay, so I am starting with a sum of 2. I can write 2 here. Since I have a lot of room on that x axis, I'm going to skip one each time. So I have 2, 3, 4, 5, 6, 7, 8, 9, 10. I know. And then 16 is off to the side here. But 16's probability isn't very large, so it's okay. I did that on your assignment too. I went off the graph a little bit.
I have a question.
You have a question?
When you're
Oh, when I'm done? Why, are you done already?
done.
Did you use fractions here?
Yeah.
That's fine. Was that your question?
Yeah, I'll just show you how I do
It should look the same.
Okay.
All right, so then I just have to graph each of these. So with 2, my probability was 0.02. Dropping my pen. So I just have to go up to 0.02. For 3, my probability was 0.03. So that would be halfway between these two. Create that bar. 4, go up to 0.05. 5's probability is 0.06. That's right here. 6 is 0.08. 7 is 0.09. 'Oh, did I skip one here?
6, 8, 9. You have all your numbers.
Oh, I was looking at these ones, yeah. 8 is 0.11. 9 is 0.13. Okay, and then 10 is where it starts going back down. So with 10, I have 0.11. 11, 0.09. I did that too. And I got really confused. Yeah, you're looking at the top one. 0.08. 13 is 0.06. 14, 0.05. 15, 0.03. And 16 is 0.02.
Yeah, it is. You're doing a great job.
Thanks, Tegan.
This is actually really easy.
That's good.
I just gotta think of something.
All right, so since this probability distribution was discrete and we were able to count it, you can see how it makes that symmetric type graph. Okay, so they all will kind of make that symmetric graph. So your highest probability is usually the one in the middle. So I mean, if you were, not that you would bet or anything, but you would want more terms in the middle there. Okay? Does that make sense? Do you understand how to find the frequency and the sum? How I did that, right? You will have to do that on your assignment. For your assignment, it doesn't include some of the numbers. Okay, so they took out like a 2, a 9, and an 11 on there, so you have to be careful so it doesn't go in order like this one does. You just have to be kind of careful as you do it. The last part at the bottom here says an experimental probability distribution is a distribution of probabilities estimated from experiments. Simulations can be used to construct an experimental probability distribution. When constructing this type of distribution, use the frequency of occurrences of each observed value to compute its probability. With small sample sizes, experimental distributions may vary greatly from their associated theoretical distributions. However, as the sample size increases, experimental probabilities will more closely resemble their associated theoretical probabilities. This is due to the law of large numbers, which states that the variation in a data set decreases as the sample size increases.
Do you think we should have a school library?
No.
Or not?
Last thing I do want you to look at, if you were to add all of these together, it should equal 1. Okay, so if you want to check your probabilities, if you add them all together, it should equal 1. Okay, your probability needs to equal 1 when you have everything together. Okay, unless there's some kind of rounding error, then it should get close to 1. But your fractions all together should add to 1, for sure. Does that make sense?
Yes.
Yeah? Great.
Don't you think it would
so-
be a good idea to have 1%? I don't think these windows are going to save us. I'm just saying. It's a possibility.
So the first 4 problems here, you're finding the random variable.
It still shows you this.
The first 4, find the random variable, so state what x is, and then whether it's discrete or continuous, so like the first 2 problems we did on the note sheet. And then number 5, that's where they're missing some numbers in that wheel shown at the right. You don't have a 3, you don't have a 9, and you don't have an 11. So you have to be careful with your sums and with your frequency in that case. And then the table for that is on the back, or the graph for that is on the back. And then there is, number 6, you're just using the table to do the prize money frequency and relative frequency.
Why is there an extra box?
What? There's not an extra box.
Yeah, there is.
Yeah, there is. What do you mean?
There's
For number 5.
1, 2, 3, 4, 5, 6, 7, 8 things on the
And there's
wheel.
9
Have you ever seen those?
There's 8 things on the wheel and 9 boxes. Uh-oh.
Well, you need the sum. You need to spin it twice and get the sum. It's not just each number as the sum. You need to spin the wheel twice to get a sum. So your lowest value is going to be 4 because your smallest number is 2. When you spin the wheel twice, if it lands on 2 and 2, the smallest value is 4. So you should start that sum as 4.
Oh, gee.
And then do 2 to the next smallest number is 4. So 2 plus 4 is 6, so that would be your next sum. 2 plus 5 is 7. 2 plus 6 is 8. So that's how I would do it. Just take your smaller value and then go around to each one to find the sum for that. and then go to the next smallest value, then go to each one, find the sum for that one. Because you should fill in all of those boxes.
1, 2, 3, 4, 6, 7, 8, 10, 12, 14.
Yep. And then you go to 4. So do 4 and 4. Did we already do 4 and 4? Yep, you already have that one. So 4 and 6, did you have 10?
Yes.
Okay. 4, 7.
Well, or that's 11.
Yep. You need 11 in there.
That's the whole part.
There's a second table below there. So it's continued on the next one.
Oh, okay.
So then 4, 8 was 12, you already had that. 4, 10 is 14, did you have 14? Yes.
Yes.
And then 4 and 12 is 16. Give me a 16.
The highest number is 24.
Yes.